And all of this stuff that we're doing in chapter 2, which we should be done with this week, is just sort of preparatory, just kind of refreshing the memory about some math basics. And then we'll get into more sort of business applications next week, probably. Okay, an exponent is a little superscript like this 3 on the A here. That's an exponent, right? So in that expression, A is called the base, 3 is called the exponent. And at first blush, exponents are an abbreviation for multiplication, right? So if I want to write 6 times 6 times 6 times 6 times 6, it's kind of a pain to write all of that out, right? If there's 10 factors or 100 factors, it's really a pain. So we just abbreviate this by writing 6 to the 5th power. And that's how you read that, 6 to the 5th power. We'll define anything to the 0 power to be 1, right? So that's a definition that we make to make all the algebra sort of work out, right? So these abbreviations make some sense. We define 6 to the 0 to be 1. And of course, 6 to the 1 would just be 1 factor of 6. So that's just equal to 6, right? So these two special cases look that way regardless of the base, right? Anything to the first power is itself, anything to the first power, anything to the 0 power is 1. A to the 2 will usually read a squared. A to the 3 would sometimes read a cubed. And after that, we'll just say 4th power, 5th power, whatever. Okay, great. So what does that mean? Notice the obvious difference, right? The exponent is now negative. You can't multiply 6 by itself a negative number of times, right? So we need sort of a new understanding of that. -5, anyone? No, good. You're on kind of a good idea there, though. 6 to the -5 we'll define as 1 over 6 to the 5, right? It's the reciprocal of 6 to the 5. So here I think are some negative exponents. Right, a to the -2 is 1 over a to the 2, a to the -4 is 1 over a to the 4, and so forth. Again, these notes that you're looking at, I will post these on the page in Canvas for this section of class. All right, so now we can make sense of any exponent as long as it's not a fraction, right? You know, 1, 2, 3, 4, no problem. 0, no problem. -1, -2, -3, no problem. So what is? Let's start with like the simplest fraction, 1/2. What's 6 to the 1/2 power mean? Anyone know? Go ahead. Aiden, right? So multiply 1 and divide it by 2, so the result would be 3 then, not quite. We'll define 6 to the 1/2 to be the square root of 6. We'll recognize that symbol, right? That's the square root symbol. So that's the number that when you square it, you get 6. Now, we need a calculator to figure out what the square root of 6 is. It's not a perfect square, but there's some number out there that when you square it, you get 6. And similarly, 6 to the 1/3 power will be the cube root of 6. That's the number that when you multiply it by itself 3 times, you get 6. And again, that's some weird decimal that we need a calculator to figure out. Right? To figure these kind of things out exactly, it has to sort of be rigged nicely, right? For example, what's 16 to the 1/2 power? Now that we know what the 1/2 power means. Yeah. Again? 4. Good, 4. Right? It's the square root of 16, which is just 4. Okay, and 6 to the 1/4 power is the 4th root of 6, and 6 to the 1/5 power, and so on and so on and so on. You can figure these out on a calculator. So if I go to Google Calculator here, most calculators on their face have a square root button somewhere, so you can do square roots directly. But what about like, you know, the 3rd root of 6 or something like that? Well, roots are powers, right? And you can enter any power you want. On Google Calculator, it's this X to the Y button down here. So if I want to do 6 to the 1/3, I do 6, hit that x to the y button, and you can see how a little subscript shows up. If your exponent is at all complicated, that is, if it's not just a single number like 5, I strongly recommend you use parentheses, right? Just to keep all that group in the exponent. So I'll go ahead and type my parenthesis, 1 divided by 3, right? Because that's 1/3 is 1 divided by 3, and then click the blue equal sign. And so that's the number. And so now if you took your calculator and you did 1.817 times 1.817 times 1.817, you should get about 6 up to round up there, right? It's the cube root of 6. Okay, so what about kind of the only thing left here is how to make sense of a fraction if the top isn't 1, right? 1/2, 1/3, 1/4, 1/5. Okay, we understand all of those. What about like 4/5? What we'll do is we'll use the bottom number as the root and the top number as the power, right? So a to the 4/5 is the 5th root of a, all raised to the 4th power. And this is consistent with what are called the laws of exponents, which we'll come to see at the bottom of the screen in just a minute, right? So a to the 17/3, bottom number root, top number power, cube root of a to the 17th. Now, in terms of actually computing these, like if you had to compute, 500 to the 17/3 power, this is the more useful thing, right? Because you're going to go to your calculator and type 500 exponent 17/3, and that's going to give you your answer. This part is just useful for understanding what it means, right? For what it is that you're calculating. Okay, so that's just a bit about the meaning of exponents. So let's do a quick couple of examples. Let's start with the bottom one here. 3 to the negative 4 power. Is that big enough? Elise, can you read all that? Yeah. A little bigger? Sure. Let's try. Okay now? Okay. So what is 3 to the negative 4? Good. 1 over 3 to the 4th. And how would I figure out 3 to the 4th? So let me catch up to what Amanda just said. All right, 3 to the negative 4. 1 over 3 to the 4. And how do I figure out 3 to the 4? Okay. Yeah, 3 exactly. 3 times 3 times 3 times 3. And again, right? And so now you could, do that by hand on a calculator or whatever. It comes up to be 81, I think. Again, when I'm throwing out questions in class, I'll never throw you a question where I expect you to do like a complicated calculation in your head, right? I'm usually looking for you to just tell me what to do. So a good answer when I say, how do I do 3 to the 4th? Is to say, well, you do 3 times 3 times 3 times 3, right? You don't have to actually do that multiplication on the spot here. I mean, if you can, that's great too, but not a big deal. Okay, so that's 3 to the negative 4th. What about the other one, 8 to the 4/3? Can someone tell me what that means?
So it's, you take the root of 8, you put the 5 on the left and the 4 on the right.
So back up to what you said initially, you take the root of 8. Yeah. What root of 8 do you take? No, it's go ahead. The bottom number root, right? So it's the 3rd root because the 3 is the denominator in the fraction, right? So I'm going to take the 3rd root of 8, and then I'm going to raise that to the 4th power, right? Bottom number root, top number power. What is the 3rd root of 8? 2, good, right? Because it's the number that when you multiply by itself 3 times, you get 8. Right? Notice how we do it's in parentheses first, right? So first we take that cube root, and now what is, how do I get 2 to the 4? Madison, do you know what's 2 to the 4? Yeah, exactly, good. It's 2 times 2 times 2 times 2, and that's 16. Questions so far? Okay, great. The laws of exponents. I am just going to throw these out all at once. It looks like a blizzard of A's and M's and N's. And the good news is that your objective should not be to sort of memorize these. There's not much value in being able to just kind of regurgitate these laws. What we want to be able to do is use them to work with expressions that have exponents, right? So when you have more than one exponent in the same expression, very often these things can be used to simplify the expression, to get it into a more useful form, etc. So real quickly, if I do something like a to the 3 times a to the 2, right? Yes. Exactly. Add the exponents and get a to the 5. What's your name again? Carolina. Let me catch up to Carolina for a minute, though. What this means, of course, is a times a times a. That's a to the 3rd, right? And then a times a, that's a to the 2. And how many a's do I have? 5, right? So the result is a to the 5. And that's why when you multiply powers of the same base, add the exponents. Okay. Again, you should know how to simplify that to a to the 5th. You don't need to be able to sort of, reproduce this. I mean, you can always look up the rule anyway, but okay, there you go. So that's the first law of exponents. If I do a to the 2 and then raise to the 3, so this is a little different. Right here I have like 2 powers. Again, if I just interpret what this means, this is a to the 2 times a to the 2 times a to the 2, right? Because that's what it means to raise something to the 3rd power. You multiply by itself 3 times. And this is a times a times a times a times a times a. And how many a's do I have? 3 copies of 2 or 6, right? And what did I do to the exponents to get that? I multiply. So when you take a power of a power, a to the m to the n, you multiply the exponents. And again, what we need to be able to do is recognize that for an expression like this, it's equal to a to the 6, because what I do is I multiply the exponents. If I have an expression like a to the 7, that's a, over a to the 4. So this is like the 3rd line here, where I have a quotient of powers of the same base. Again, if I write out what this means, this is a times a, right? That's 7. And then 4 copies of a in the bottom. And what happens? What can I do to that fraction? Go ahead. Say it one more time. Yeah, I can eliminate or cancel factors. Exactly right. Right? How many can I cancel? 4 in this case, right? So I can cancel these 4 a's, these 4 a's. And what's left? I have a to the 3rd, right? There's 3 a's in the numerator. And what's the effect? I subtract the bottom exponent from the top exponent. So I wind up with a to the 3 power, right? You don't have to write out this cancellation every time. This is just sort of at the beginning to show why these things make sense. We need to be able to take an expression like this and realize that it's equal to a to the 3rd, right? And what I'm doing here is I'm subtracting top power minus bottom power. Okay, the other 2 maybe I'll just talk a little bit about the fourth one and we'll leave the fifth one to take on faith. If you have something like A times B all cubed, right? So now I have a power where the base is a product. Again, if I write out what this means, anything cubed is that thing times itself 3 times, right? Whatever you're cubing, you multiply it by itself 3 times. Well, multiplication is commutative. There's a fancy word. What does commutative mean? You've heard that before. You can do it in any order you want, right? And it's associative, which means you can group it however you want. So if you have like a big long product, you can rearrange the order of the factors however you please. So I can rewrite this as A times A times A, because I have 3 A's, times B times B times B, because I have 3 B's, right? And the first thing is A cubed, and the second thing is B cubed. And what's the effect? I raise each factor to that power, right? So this is always true, and this is true even if this power is a fraction, even if these things are, the terms in the product are complicated, right? The same basic rule always applies. And similarly, when you raise a quotient to a power, you raise top and bottom. All right, let's look at a couple of quick examples. Think for a minute about this one. Right, I'm going to give you a couple minutes to think about that one. The goal is to try to simplify it and write it as an expression that only has one exponent. Right now, there's kind of 2 exponents. All right, let's see. They don't make any progress? Yeah, the first one, right? Excellent, right? So let's talk about how we got there. Good job. Here's the expression, right? 5z squared all squared. So the first thing I'm going to do is recognize that this is a product to a power. So I raise both factors to the power. So this is equal to 5 to the 2 times z squared to the 2. Right? Each factor in the product gets raised to the 2. What's 5 to the 2? Anybody know? Okay. 25, right? Just 5 times 5. So that first one, I can simplify no problem. And then the second one here, I have a power to a power, so I multiply the exponents, right? So z to the 2 times 2 is z to the 4. And we come out with exactly what we said a minute ago. Okay. You could also have thought, well, this is going to be 5z squared times 5z squared. And whenever I have a product where it's all multiplication, I can rearrange the order however I want. So I can bring the numbers to the front. So that was always 5 times 5 times z squared times z squared. 5 times 5 is 25. Here I'm going to add the exponents because I have powers the same base. 2 plus 2 is 4. And of course, I get the same answer. Right? Often there's more than one route to simplifying an expression. I think the first way is a little bit better, but it doesn't matter, right? You get the same expression. Questions? Okay, try the second one, but in the second one, just apply one law of exponents and then stop. Go ahead.
So is it like I? The letter is I.
The letter is I, yes.
Okay, so it would be 1 plus I and the 2017 minus plus 12. So it's 1 plus I in the power of 29.
So what was the final power again?
So it's the first law. Just add both of the exponents.
Excellent, right? So I add the exponents, 17 plus 12 is 29, and I wind up with 1 plus I to the 29 power. Now, we know what this means, right? 1 plus I to the 29 power is 1 plus I times 1 plus I times 1 plus I 29 times. Right, and I only write that for emphasis of what the exponents mean. That, you know, it is in theory possible to sort of multiply all that out. It's way more output than out here. But we should know what the exponent means. All right, let's try the last one. Oh, it's not the last one. Let's try the next one. Like, what was the last exponent? What? Good, nice job. Okay, so looking at this, right, the first thing I realize is I can reduce the 35 over 14. I can also write this, I can kind of split this up into two fractions if I want to think of it that way. Right, because when you multiply fractions, you just multiply straight across the top and bottom, right? No common denominator in multiplication. That's only when you're adding fractions. That includes when you variables in the fractions. Okay, so here I have a quotient of powers of the same base. That's one of the laws of exponents, right? You subtract the two exponents, and that's going to come out to be exactly what Skylar said, x to the 3 power, 7 minus 4. Here, I suspect you did this on a calculator, right? 35 over 14 comes out to be 2.5, so that's fine. You can do that. You can also recognize that 7 will cancel top and bottom, right? You can reduce the fraction. And if you reduce the fraction, you get 5 over 2, right? 35 is 5 times 7, 14 is 2 times 7. And 5 over 2 and 2.5 are the same thing, so it doesn't matter. Right. All right, and think about the last one. I think this is the last one. All right, any progress on this? But you're not in Delaware here. Yeah, I got the name right, but you're not sure. Yes. Ma'am. So let me pause, Carolyn. Let me pause there. So that's an interesting idea that actually leads into the next thing that we're going to talk about. So here I have 5a to the 5th, here I have 9a to the 6th. Can I combine those somehow and get like 14a to the something? This is no in this case, right? Because they're not what are called like terms. And we are going to talk about like terms in just a moment. Right? A term is a power of a variable with a number in front of it. That's it. That's what a term is. So here are some terms. 2x to the third is a term. 7e to the sixth is a term, right? Number, power of a variable, that makes a term. A number by itself qualifies as a term, because 15 is technically 15 times x to the 0, because anything to the 0 is 1, and 15 times 1 is 15. So it counts, it qualifies as a term. Two terms are like if the variable is the same and the exponent is the same, right? So this number up here is sometimes called a coefficient. So in this term, 2 is the coefficient, 7 is the coefficient, 15 is the coefficient. The variable obviously is the letter, and the power of the exponent is the superscript number. If the variable and the superscript are the same, the terms are called like terms. So none of these are like terms, right? Here are some like terms. 6q to the 4th and 19q to the 4th. Those are like terms, right? Like terms only differ in the coefficient, nothing else, right? If the variable is different, the exponent is different, they're not like terms. And only like terms can be combined with addition. So looking back at the top here, are these two, this and this, are they like terms? No, right? Because the exponents aren't the same. It's a 5th power in one and a 6th power in the other, which means you can't combine them. They have to sort of stay apart. All right, that was a good idea because it would have been nice if you could combine them. That would have simplified nicely. So what's another strategy for this one? And then we'll talk a little more about combining. Go ahead. Okay. If you have, let me back up a little bit on this one. If you have this problem, right, it's a little fraction addition problem. What's the solution? Yeah. 13/4, right? Because why? You have a common denominator, right? 4 denominators, so you can just add the numerators and get 13/4. And the reason I raised this example, which looks like it has nothing to do with what we're talking about, is that you can also go in the reverse direction, which looks weird here, right? Why would you take 13/4 and split it into 2 fractions? But here, I have, when you have variables involved, that becomes a more viable strategy. I have a common denominator, right? They're all both over the same denominator. So I could split them up and write that like this: 5a to the 5th over 3a to the 3rd plus 9a to the 6th over 3a to the 3rd. And notice that this looks kind of like this, except that the terms are more complicated than just numbers. But I have the same denominator in both, so I could always combine them, and I'd wind up right back there where I'm. The advantage now is that hopefully these two things individually, and what was your name again? Sophia, and this is what Sophia was talking about, sort of simplifying this one is a little more doable, right? So how did you simplify this one, Sophia? Good. Excellent. Right, so the 9 and the 3 reduced to 3, right? You just reduce the fraction. And I subtract exponents, right? Because it's a portion of powers the same base, and 6 minus 3 is 3. Okay. Here, can you tell me how the A's simplify in the first stack there? Right, because again, I subtract exponents. 5 minus 3 is 2. Notice that 5 and 3 don't reduce any, right? 5/3 is just 5/3. So I just get 5/3 a to the 2. Questions about that? Okay, let's go ahead and, oops. Show that on the screen. Okay, so there's sort of 3 pieces of algebra that we're extracting from a much bigger subject that's most useful to us going forward. Piece 1 is working with exponents. It's probably the biggest, most complicated piece. Piece 2 is combining like terms, which we started to talk about. We'll talk about a little bit more now. And piece 3 is just using calculators to evaluate reasonably complex formulas. Right, so using a calculator to do, 57 plus 32 is not a big deal, it's pretty straightforward. But if your formula has more pieces and variables you're plugging in for in parentheses, there's a little bit more art to it, though not much more. All right, so as we just said, like terms have the same variable and the same exponent. You may find yourself faced with a whole string of terms where some of them are like and some of them are not like. And what you should be able to do when faced with a string like this is identify what terms are like and combine them. And then that's really it. That's about all that you can do with it. So looking at the thing that I just put on the board over here, can you point out 2 like terms in this to me? Please. Good, excellent, right? So those 2 are like terms. And how do you combine them? I should say, when you combine them, what do you get? Good, right? So careful with your signs. -6 and -5 is -11. So when I combine these 2, I get -11 x squared. Any other like terms? Yeah. Excellent, good, right? 5x to the 10th and 2x to the 10th are also like terms. And when you combine those, what do you get? Do you know? I'm sorry, I can't read. Good, right, 7x to the 10th. Right, and that's it for like terms. None of the other terms are like, so I just carry them down. What am I missing here? -14. And then a plus x. Okay, questions about what happened? All right, and it simplifies things a little bit. Instead of 6 terms, I have 4. So I guess that's a little better. Here's another example on the screen, right? In this string here, these 2 terms are like, same variable, same exponent. This one is not, the p squared. So I can combine the first 2, and 8 minus 6 is 2. And that's where the 2p cubed comes from here. Questions so far? Okay, using calculators and formulas, here's an example of what I have in mind. Right, this is actually a kind of computation that comes up a lot in computing the growth of money and value over time, as we'll see eventually. And this is obviously something you would do in a calculator, right? So my only point here is to emphasize that you have to be a little careful entering on a calculator, because if you don't sort of get the parentheses in the right place, you'll wind up getting the wrong. I mean, the calculator will do the computation right, but if you tell it to do the wrong computation, then that doesn't help matters any. So when I go to enter this on Google Calculator, let's see if we can get both on the screen at once here. There. Okay, so let me first clear out. So I have 4,500 out front, right? Now, this is multiplication, right? When the number's right next to the parenthesis like that, that's understood to be multiplication. So I'll go ahead and hit times. Then I have a parenthesis. 1 plus 0.079 divided by 365. Close parenthesis. Now, already a question comes up to me. In here, do I need any parentheses? Right? Because I have two operations. I have a plus and a divided by in there. Do I need any other parentheses, or will this work? So yes, that will be fine. The answer is you don't need them. Is that what you're going to say? Exactly. You don't need them, but they also don't hurt, right? If you're not sure about adding parentheses, I would go ahead and add them, right? It will almost never mess things up, but if they're not there when they need to be, that's the problem. Here, they don't need to be because division comes before addition, so the machine's going to do that calculation first, which is what you want based on this expression over here. Okay, so let's keep going. I want to raise this to a power, right? You can see when I hit the X to the Y on Google Calculator. Now, every calculator is a little different, so if you're using yours or a different online one, that's fine, but you're going to have to get familiar with its layout and its buttons and so forth. Okay, now I am going to use parentheses in the exponent. Again, here, I don't think that that's absolutely necessary. You'd probably be okay without them, but I'm going to play it safe. And then I'll just type 4 times 365, close parentheses, and when you're all done, click equals, and there's our result. When you are entering some calculation like this into a calculator, it is best not to do it piecemeal, but rather type the whole thing in and click equals or enter or whatever the button is on your calculator that does the computation. As opposed to attacking this by first doing, say, 0.079 over 365, right? Do that on a calculator and then add 1 and see what you get, right? See how I'm working from the inside out. The problem with this is, well, there are a couple problems with this. One, more steps means more room for you to make a mistake, and it's confusing to keep track of it all. Also, you accumulate round-off error, right? Because at every stage here, you're rounding off a decimal from your calculator, and that error will sort of pile up through the calculation, and it can, in some cases, make a non-trivial difference in the result. Whereas if you do it all at once, the machine will take care of that, and you'll get a very precise result. Okay, so let's see what's next here. All right, so here I have a calculation that has both variables and numbers. You can see that there's a capital P here and another capital P here. It looks like a bit of a mess, though. What should I do to make that a little simpler? Like, what's a good step to take here? I'm not looking for what the result is. You're faced with this. You want to go ahead, Neil? One more time, I'm sorry. So take, you mean this thing here? Yeah, right. So I'm going to go ahead and calculate this, right? Go to my calculator and figure out what that is. So let's see, that's 18 plus 0.172 plus 118 divided by 41. Right? I don't need any parentheses there. It'll do the division first, which is what I want. If you put parenthesis around this, you get exactly the same answer. So that's fine. Nothing wrong with that. All right. So this comes out to be, I'm going to call that 21.05. So that first term is 21.05 p, right? Because we calculated the thing next to the p. Okay, good. So now this thing's in the way a little bit. What should I do next? Okay. Yeah, good, right? Anytime you have an expression and you see like a numerical calculation that you can do, can't hurt, right? Good idea. The simpler those expressions get, the easier your life gets. So I'm going to go ahead and do that calculation in the denominator, which is 1 plus 0.9 plus 17 divided by 41. And I'll call that 2.315. Now, be careful when you round up decimals, which you will have to do. Keep a couple of places, but do the rounding up correctly. So if I'm going to round here, because the next digit's 5 or more, I'm going to bump that 4 up to a 5, right? And it's 2.315, which is my result. So that second piece here looks like P over 2.315. Okay, can I do anything else with that? What if I adjust this just a little bit? All right, those are the same thing because dividing by a number is multiplying by its reciprocal. Right? That's universally true. That's what division is, multiplication by the reciprocal. So if you're dividing by 2.315, you're multiplying by its reciprocal, which is 1 over 2.315. What should I do now? Yes. So you're right. Mariana's observing that these are like terms. Same variable, p, same exponent, 1, right? If there's no exponent there, the exponent is 1. So I'm going to be able to combine them. That's good. I would take a little step though before I even did that.
Or turn it into a decimal?
Yeah, I would just make this into a, that's not absolutely essential. You could add it as it is if you want, but it will look a little bit simpler to me. Let me clear this. 1 divided by 2.3. There we go. So 0.432, we'll call it. And now to combine those terms. Go ahead, Don. Say it one more time. What do you mean? Use the same number of decimal places? You could do that. I mean, again, not essential, but we could go ahead and let's just call that 0.43 then. Now I have the same number of decimal places. Now what? Now? Right? Good, exactly, right? So what's your name? Tatiana. So all Tatiana did was combine the two coefficients because that's how you combine like terms, right? And when you do 21.05 plus 0.43, you get what Tatiana just said, which is 21.48. Okay, so that's simplified a lot, right? This is the original expression, which is a mess, and it reduces all the way down to just a fairly simple term. All right. One more, we'll practice a little bit, that'll be good for today. So another thing that sort of falls under this heading, one is kind of using calculators to both just compute things straight up, using calculators in conjunction with a little bit of algebra to simplify some algebraic expressions, and importantly, using calculators to plug into complicated formulas, right? So finance is awash in kind of complicated formulas like the one that you see on the screen there. And it will happen a lot in this class that we'll have this formula and we won't often worry about sort of how to get it or sort of working with the formula, but we'll want to use it, right? These variables will have meanings. One variable will represent like the interest rate and one the amount of time that's gone by. We'll get to all that later. For now, suppose I have all this identified, I have the formula, and I want to plug in values for some of the variables in the formula. And you can see I have 4 variables in the formula total, right? There's a P, an F, a capital N, and an I, right? So I have 4 variables total, which means if you have values for all but one, you can plug in, and if the formula is not too bad, solve for the last one. So here, I'm being given values for the F, the I, and the capital N, and I want to find the other variable, the P. Okay, so in order to do this, right, all I do is I take these numbers and replace the appropriate variable, being sure to keep things kind of exactly where they are. So in the numerator, that F is going to become a 10,000. Right? And then in the bottom, 1 plus I is 1 plus 0.05. Now 1 plus 0.05 is 1.05, but usually when I plug into a formula the first time, especially if it's a little bit complicated, I'm not going to do any computing or simplifying. I'm just going to plug everything straight in, and then we'll worry about that in the next step. Okay, n is 18, so this is to the 18th power. And there's a minus 1. Well, this gets divided by 0.05. Right, so step 1 is get the values into the formula where they belong. Now I have something that's kind of similar to the first example, right? It's all numbers. I just need to load it into a calculator and get it done. So let's see if we can do that. So we'll clear. The top is 10,000. What should I type next? Parenthesis, right? Because I want this whole thing, maybe it's better to look over here. I want this whole thing to be in the denominator, right? So that's going to be in parentheses. All right, then I'm going to do another parenthesis. And I'll do 1 plus 0.05. Well, we'll sort of type and see how it goes here. right? And then I want to raise that to the 18th power. When you're done in the exponent, if you use like a right arrow key, it should get you out, or you can just go ahead and click in the formula here. And that's what, -1. And I can see, and I think Mariano was starting to mention this, we're going to need another set of parentheses, right? Because I want this thing to be the numerator. I want to keep that together as the numerator, but I want the whole fraction in the denominator. All right, so I'll go ahead and close off those parentheses. And then here, I'll click in the formula and add, whoops, that's not what I wanted. Oh, it's not letting me click in the formula. That's unfortunate. All right, well, let's go back. You know what, let's just clear the whole thing. And try again. Now I know I need 1, 2, 3 parentheses. 1 plus 0.05. Those parentheses raised to the power. I'm going quickly because we did this already. -1, close parenthesis. Now I'm ready to divide by the 0.05. There. Another advantage of typing the whole formula in at once is you can kind of look at it and make sure that it looks right, and you can see the whole thing. You're not missing pieces of it. So I click equals. There's my result. Questions about anything? All right, let me stop this.